Hey everyone, let's talk about the idea of an equivalent impedance away from a load. So you notice I've drawn here a typical transmission line, and Z equals 0 is usually referenced here at the input points to this load. So naturally there's some incident wave striking this load and a reflection with some energy getting absorbed inside or transmitting through. And so by definition, that load impedance is simply the voltage divided by the current when evaluated at this point here at 0. And of course, similarly, we have this idea of a reflection coefficient, which was simply the amplitude of the reflected wave divided by the incident wave. Now, a common thing that might happen in transmission line theory is to say, what happens if instead of this being my load, what if I kind of crumpled the cable up in with the load and put it into a box? Because I don't necessarily know what's inside of this load. There could be anything at all. It could be a bunch of capacitors and conductors, but it'd also be an antenna with 9,000 feet of cable bundled into a tiny little black box here. I don't necessarily know physically what's here. All I know is that it has an equivalent impedance, which I evaluate from the voltage and the current. So what that implies is, what if instead I imagine creating a box here like so, and I just bury all of this stuff inside of this box, a distance of say negative L, so negative to the left, away from my original load. So what happens if I take some arbitrary load and I compactify it with some particular length of cable to create a new equivalent load? So you've probably done this, you've seen this idea before in some of your other classes with this notion of a black box, right? So it's just a box. I don't necessarily know what's inside of it. All I know is that there's some voltage and current at its inputs. And it led us to this notion of, say, Thevenin equivalent circuits, right? So a similar analogy in microwave engineering is this idea of an equivalent impedance of this new circuit. So all I've done is taken my original load, added some length of line, and asked what is the equivalent impedance of that new load, and what will my new reflection coefficient be accordingly. So in this sense, it's useful to define this notion of what we call an input impedance, right? The equivalent input impedance looking down these terminals of this little black box here. So I'm going to define my input impedance as my load impedance evaluated at negative L, which will simply be V tilde at negative L divided by I tilde evaluated at negative L. So that's the definition of my new impedance at this point here. And I also want to talk a little bit about this notion of an equivalent reflection coefficient, right? Because remember, the definition of the reflection coefficient is just the forward propagating wave divided by the reverse propagating wave, evaluated at a particular point relative to the load. So originally we just did it here at Z equals 0. Now we're just going to stretch it out over here. So remember that the voltage along load, or along a transmission line, was V naught plus e to the minus j beta z plus V naught minus e to the plus j beta z. So typically when we evaluated the reflection coefficient, we did it at Z equals 0. But if we just move it down a little bit, we're just going to essentially take the ratio of this thing to that thing over there. So I'm going to say gamma of negative L is simply the reflected wave magnitude, which is V naught minus e to the minus j beta L. So I'm putting in L for Z, divided by V naught plus e to the, so a negative L, negative negative gives me plus j beta L, like so. So you look at that, and that's actually the following: V naught minus over V naught plus times this thing, which is e to the minus 2j beta L, which is, let's see, well, if we can squeeze this in here, gamma of 0, I can't quite fit that, so we'll write it over here, is equal to gamma of 0, so that's the right there evaluated here, and then there's just this little phase term, e to the minus 2j beta L, like so. So let's write this out, gamma of negative L is equal to this thing here. So this is an important relation in transmission line theory because it just says that my equivalent reflection coefficient at some distance away from a load is just the original reflection coefficient multiplied by this little phase term. So graphically, that actually creates a nice intuitive picture because what you can imagine is the following. Let's suppose I have a plot here. So this is going to be a polar plot where this is, this is going to be the real axis here, and this is going to be imaginary here, and I have some reflection coefficient here, which I'm going to call gamma of 0. So this is my original reflection coefficient. Remember, it's a complex value in the complex plane. And if I just move away from the load, all it's going to do is add this little phase term here to my original reflection coefficient. So if we draw this out here, remember there's some original phase here, and I'm going to add this negative phase to this term here. So all it's going to do is rotate clockwise to give me some new point down here. So it's going to have exactly the same magnitude, but just this new phase right here. So that change in phase is going to be 2 beta L. All right, so that should make sense because what you have is the phase that you collect by going down, which is beta L, and then more phase is collected in the reflection coming back, which is another beta L, which leaves you with this 2 times beta L in my accumulated phase. And which also leads to an interesting result that if I let L equal, say, lambda over 2, a half a wavelength, then what will happen is it'll go down 1/2 a wavelength, reflect and come back again to another half a wavelength to give me 1 full wavelength, which is an accumulation of 2 pi radians of phase. So what you get is beta L is equal to 2 pi over lambda times lambda over 2, which is equal to pi, and then I multiply this by 2 here because there's a 2 beta L and I get a 2 pi, okay? So an accumulation of 2 pi radians just means I come all the way back to my original point again, which means if I have a load plus 1/2 wavelength of transmission line on it, then what will happen is, as far as my reflection coefficient is concerned, nothing will have changed. And my input impedance will therefore be exactly what it was before. So let's now calculate the equivalent input impedance given this new picture. So let's see, we'll find some space here. So remember that, we'll put it here. So Z in is equal to, by definition, the voltage divided by the current. So what you're going to have is the following. V naught plus, and it's going to look like this. E to the minus j, but this isn't going to work. I'm cramming. Let's put it over here. So Z in at negative L is, by definition, V tilde of negative L divided by I tilde of negative L. Okay, so remember I have the forward plus the reverse propagating wave, which is going to look like the following. I have a V naught plus times e to the minus j beta L plus gamma e to the plus j beta L divided by V naught plus divided by the characteristic impedance, so that's the amplitude of the current. And you remember from a few lectures ago, I get a similar expression, e to the minus j beta L, only it's a minus over here. E to the minus gamma plus j beta L. So remember that negative sign is because a current moving to the left has negative amplitude there. So whereas with the voltage moving to the left would still be positive. So you look at these, the V naughts cancel, and then this little Z naught here is going to come up in front. So I'm going to get a Z sub 0 divided by, or multiplied by all this, e to the minus j beta L plus gamma e to the plus j beta L e to the minus beta plus, so all right, this is going to be a little tedious here, e to the plus j beta L. Okay, so you can leave it like that, but most references like to take it a couple of steps further. So let's rewrite that over here. So I'm going to have Z in at negative L is equal to Z naught times this thing over here, e to the minus j beta L. So bear with me, I got to rewrite all this. Minus gamma e to the plus j beta L plus gamma e to the plus j beta L. So remember now that gamma here is at the load. So I get ZL minus Z naught over ZL plus Z naught, which was gamma evaluated at 0. So what you do then is you just take this stuff and you substitute it into here. And you do a bunch of algebra. You also remember that e to the jx from Euler's identity is equal to cosine x plus j sine x. So you use this and you put that in for those complex exponentials, and you put your gamma in and you substitute and you do a bunch of rearrangement. And we're not going to bother. It's just a bunch of algebra. So I'm just going to write here some algebra will happen like so. So you can do that derivation. It's just 2 or 3 steps, and you see they're a little bit grindy. So you turn the crank on all of that, and you eventually get the following expression. Z in at negative L is equal to the following. You get Z naught, and I'll get ZL plus J. Z naught times the tangent of beta L. So remember, you get the cosine plus the sine, and then you divide out the cosine over here, and that's where this tangent comes from. You get a ZL plus J, or sorry, Z naught plus J. So they're flip-flopped in the denominator here, and I'll get a tangent of beta L, like so. So you notice this is kind of a nasty equation. You can slap this into MATLAB, and it will be more than happy to crunch on the arithmetic here. But this is a very ugly equation, but it has a special name. It is the transmission line impedance equation. Impedance equation, like that. Okay, so in all of its glory. So you'll get a little practice just working with this thing. It is not pretty. It's kind of nasty. And this is one of those little motivations for the Smith chart, right? Because you'll notice here, when we just thought about things in terms of the reflection coefficient, we just got this nice little spinning effect around a circle. But when I wanted to think about it in terms of impedance, I get this horrible complex fraction of loads plus characteristic impedance and this tangent of this phase factor here. And it gets really nasty. So keep that in the back of your head. Yes, you can crunch that and you'll do a few practice problems on it. But this is one of those motivators where the Smith chart starts to make a little bit more sense, right? To think about the world in terms of this reflection coefficient on this polar plot, rather than deal with the grind of the algebra and the arithmetic. But that is now the equivalent impedance of some load as viewed some distance L away from it on the transmission line.